Okay, so are you able to see my slide?
Yes, sir.
Yes, sir.
Okay, okay, so we'll start our session, and then today we will study on real power and reactive power scheduling. Okay, still we are at unit 4 only. So under unit 4, so today will be this lecture 6, and then in lecture 6 we will be studying on real and reactive power scheduling. Okay, so in briefly we have done everything. When we say about the real and reactive power scheduling, okay, it means we have to carry it out based on the cost optimization. So optimization, we have learned earlier how to carry out the optimization. We have to, there are two conditions: first equality constraint and then inequality constraint. You have to consider that and then do a optimization. Okay, but in this lecture we will see how to carry out the real and reactive power scheduling based on cost optimization. Means as far as possible, cost of your energy should be cheaped or lower way. So how we will carry it out? So we'll see that. Okay, so in this lecture we will learn the following, which cost minimization considering network constraint and losses, and one illustrative example. With one example we will carry it out. But here cost minimization considering a network constraint and losses. So earlier when we carried out the optimization, so we have not considered about anything about the losses taking place. Okay, earlier one we have just seen that uh, generator one will generate, let's say, 250 megawatt, but we have not considered any losses. Ideal case, but now when we carried out the real and reactive power scheduling, so we will have to see the constraint. Okay, so network constraint and then losses. So in last class lecture, we have just seen that equality constraint and inequality constraint. So what are the equality constraint? What are the inequality constraints? So we have not considered. Okay, just general we have done. So now in today's lecture, we will go specific losses, then equality constraint, non-equality constraint. Okay, so just call. So now what we are trying to do here is, when we consider all this, what are the equality constraint, what are the inequality constraint, and then all this, then we are trying to find the optimal power flow. Okay, so optimal power. Okay, so optimal power flow. Okay, so that we'll define first optimal power flow, and then we'll try to carry out the optimization. Okay, so now here in this slide, so what I have said is, until now, okay, till now, we have just considered a simple example. Okay, simple example. This is just simple example we have considered. We have not considered any losses taking place in the optimization problem. Okay, so in actual case, there are many variables other than generated power that need to be scheduled. Okay, so in earlier example, we have just carried out or scheduled the real power based on the generated power. P1 if it says 250, and then cost, how much cost. So we have just seen that, and then based on that, we have seen that P1 should generate 250, P2 should generate 300, and then P3 should generate 50, like this. We have scheduled like this, right? But there are many variables which we need to consider. Okay, so this may be set under the direction of system operator. Okay, so how to carry it out will depend upon the direction of system operator. Okay, so system operator has to find, as far as possible, low cost or cheap energy. Okay, so now if the quantity which is to be scheduled belongs to independent entity, so now system operator, sometime we may have to buy the energy from other company or independent entity. So example, BPC is carrying out distribution and then uh, transmission and distribution in Bhutan. But BPC is not generating. BPC has to buy from the DGPC. In such case, what you have to do is the system operator has to buy that power from that entity. Example, BPC is buying from the DGPC, and then quantity based on the price which it is sold. So now will not BPC will not go there and directly buy the power. Okay, DGPC will charge some amount. Based on that, we have to buy, right? So that also we have to consider in the optimal power flow or optimization. So that formulation of the minimum cost problem by including the network, reactive power demand, voltage, and current constraint is known as optimal power flow. Okay, so now if you're able to carry it out or formulation of minimum cost problem, including the network, okay, whether it is your network or you're using the other network or you're buying from other. And then earlier one we have only seen the active power, but here you have to carry it out the reactive power demand, then voltage, current, constraint is known as a optimal power flow. Okay, so when somebody asks what is mean the optimal power flow, actually it is a formulation of a minimum cost problem. Okay, cost should be as far as possible minimum by including that network constraint, reactive power demand, voltage and current constraint. It's known as a optimal power flow. So in this optimal power flow study, so it will also include the losses taking place in the network. How much losses is taking place in the network. Okay, so this is a basic about the optimal power flow. Okay, so now what you can do is, so for now, what we, okay, so for now, okay, so for now, so let us consider optimal power flow problem. So we'll just carry out the optimal power flow problem, considering these 5 characteristic or the 5 factors. First, we have to see the control variables. Okay, then load demand is fixed. Okay, here also we have carrying out a lot of assumption. Okay, first control variables which can be scheduled independently and are generated real and reactive power, and then load demand is fixed. So in real case this demand is not fixed, but here for our simplicity we'll try to do, okay, first with simple example. Load demand is fixed, then cost function is a function of only real power again. So we will assume that providing reactive power for maintaining voltage is free. But in real case, so again, it is not a free. Okay, so cost is a function of only real power. Okay, for a simplicity, we'll just carry out one example of optimal power flow, considering a control variables, then load demand is fixed, then cost is a function of only real power, which means we are considering that reactive power for maintaining voltage is free. Okay, so if there is no reactive power, you know that there won't be a real power. Okay, so but we are considering that only for a real power, which means servicing of providing the reactive power for maintaining voltage is free, then real power are constrained by maximum limit. Okay, which means power has a maximum, okay, real power it can generate is, let's say 230 or 290 megawatt, which means it is a maximum limit, and then voltage magnitude is constrained by maximum and minimum limit, which means voltage has a plus or minus, right? Example, if you consider in terms of per unit, there should be a maximum 1.05 and minimum it should be below 1, that is 0.975, like this. So this, with considering this, so now what we will do is we'll try to carry out the optimal power flow. But in actual practice, this is not only the factors which will contribute to the optimal power flow. There are a lot of additional constraints and variables are present. But for the sake of simplicity, let us consider only one mentioned above, which means this 5 constraint. And then I can say that for you all, as per our, so this much constraint is more than enough. Okay, so if you really want to go for a higher study, or if you really want to do for master and PhD in power system, then these factor will not be sufficient to carry out the optimum power flow. Okay, so, but for us, it's more than enough to carry it out with this, okay, characteristics or a factors. Okay, so now we'll take one example. Considering all these factors, we'll try to carry out the optimization. Okay, optimal power flow, which means we are trying to find the minimum cost. Okay, so let's say consider a two generator system. Okay, let it be generator 1 and generator 2 system which supply two loads. Okay, it's supplying two load. Okay, two generators supplying a two load at buses 1 and 2. So we consider this as a bus 1, this as a bus 2. Okay, so let's consider a two generator system which supply two loads at buses 1 and 2. Okay, this bus 1 and then bus 2. So now question it is just they are asking is compute the minimum cost real and reactive power schedule of the generator if the cost of real power is this much. Okay, for generator 1 cost of real power is C1 is equal to 50 into P1 plus 300 into P1 square. Okay, this is a question it has been given. If the cost of the real power then of the generator 1 is given by C1, then generator 2 is given by C2. Why it has been written this? So you know we are including fixed and variable costs. Okay, then reactive power is assumed to be free, means whenever required it's supplied. But actual case it is not like that. But here in this problem, they are saying please try to find the minimum cost of real and reactive power schedule. Okay, if generator 1 cost is given by C1 and generator cost 2 is given by C2, and then assume that reactive power is free. Okay, whenever required it will supply the reactive power. And then other constant they are saying is this condition limits are applicable, means voltages at both the buses, bus 1 and 2 should be minimum should be 0.975 per unit and maximum should be 1.025 per unit. Okay, so when you carried out the optimal power flow or optimization, it has to fulfill that voltages at both the buses, bus 1 and 2 should be 0.975 and then 1.025. Maximum should be 1.025 per unit and minimum should be 0.975. Okay, this is a condition it is they are giving. Okay, so then another one is generated real power for each generator should be 3 per unit. So each generator should generate 3 per unit, means this is also one sort of the constraint they are mentioning. Okay, so then reactive power capability is assumed to be unlimited, which means whenever required reactive power is provided. Okay, so this is a condition given in the question. Okay, so based on that what we have to do is we have to compute the minimum cost. Okay, minimum cost, so that we will schedule the real and reactive power. And then here all values are given here, R and X. R plus Jx, R value is 0.02 plus J value is 0.1, and then PL1 and QL1 it has been given here. Okay, all value it has been given. This will be given, don't worry. Okay, so you cannot assume your own, but this all value will be given and this condition will be given. So based on this condition, then what we have to carry out is optimum power flow. Okay, so now how you will do now? It's same like optimization in earlier previous lecture. So we can say that here it is not given that subjected to this and then all. Okay, so only cost function is given and then some condition it has been given. So from there you have to identify which one is equality constraint and which one is inequality constraint. And then already we have learned the definition of equality constraint, and also we have learned the definition of inequality constraint. So in such case, if you get such type of problem, then what you have to do is you have to frame first this cost function. Total cost C will be equal to C1 plus C2, and this has to minimize, right? When you minimize, it has to fulfill the certain objectives or the certain constraint. So what are the constraints? Here directly it is not given as equality constraint and the inequality constraint. So actually in optimization you have done like this, J, X, comma, U, okay, and subjected to it will be given G, X, comma, U, and this is equality constraint. Again, optimization means we have to consider for inequality constraint H minimum should be less than or equal to h x comma u. It should be okay. So this you have to do, you know that, but here it is not given directly as a g x comma u and that inequality constraint. But what you have to do is, so in such case you have to form this equation c equal to c1 plus c2. So c1 c2 is already given in the equation, and then this has to be minimized. But when you minimize, what it has to get is, you have to fulfill the certain condition given in the quotient. So what are the condition it has been given in the quotient? So you see here, read very carefully. Real and reactive power is assumed to be free. That's fine. Then voltage limits are also given. Voltage at both the buses should be, it has maximum and minimum value, and then generator real power should be less than 3 per unit, means each generator should generate 3, and then also some other characteristic has been given. Okay, so that is impedance has been given, then load power, okay, both reactive and the active power has been given for both the buses. So now in such case, what you have to frame is, so now you have to identify which one is equality constraint and which one is inequality constraint. So now by definition, you know that equality constraint will be related to power, right? Power. Then inequality constraint, you know that, like voltage and then current. Are you remembering that? Which has a maximum and minimum? But okay, so now you have to identify that, and then for bus 1, so we have to find that P1 minus PL2. Why P1 minus PL2? This is because it is generating P1, and then load power is PL1, and then you know that if you have this type of diagram, then how you will find is P1 is a real power of the generator 1, and then PL1 is the real power uh, of the load 1 at the bus 1, right? So we have to minus that, and then you have to find how much power can be exchanged between generator 1 and generator 2. So which means you can find by this equation, right? V1 into V1 cos phi by Z minus V1 into V2 cos phi plus del 1 minus del 2 by Z equal to 0. So then another thing is, another constraint is, now we have to see from another side, generator 2, PL2, and then same case. So here it will be V2 square cos phi by Z minus V1 into V2. Okay, so del 2 minus del 1. So you have to take note of this. And then this one, you know how you have got it this. Okay, so then this has become a equality constraint, that is G x comma U is subjected to this one. When you minimize the cost, it has to fulfill that. Then another one is that H minimum. Okay, so H minimum should be less than or equal to H x comma U should be less than or equal to H maximum. Okay, so in this, so it has given voltage, right? So voltage, it at the both buses, it should have maximum is 1.02 and the minimum is 0.95. So that's why it has V1 minus 1.02, or actually it is V1 is less than, okay, at the max 1.02, but when you take it to right hand side or left hand side, so you will get minus and then less than 0. And similarly, V2 should also be this value, and then 0.975 minus V1 should be, this is a minimum value. Okay, so for both the cases, and then for both the cases, power should be 3, right? Less than 3 per unit, and then Z. Okay, so that Z here, if you really want to substitute, then we have to find that Z is given by R plus JX, and the value of R and X is given in the quotient. Then you can find the phi is equal to tan inverse of X by R. Okay, so if you know this, okay, so then here we have to frame this condition, then only we will be able to carry out the optimal power flow or optimization. Okay, so this all condition, you read the question and then you will get from the question. Okay, so it will be given in the question. So just we have to frame in mathematical way so that you will be able to identify which is equality constraint and which is inequality constraint. Okay, so here all these explanation are given best. Okay, so already I have explained, so you just read this explanation, you will understand that. Okay, so now we have formed that. After that, how you have to carry out the optimization or optimum power flow is you have to form a composite cost function. Are you remembering that? We have to find a composite, or we call it as argumented cost function. To obtain the solution to the problem, we first form an argumented cost function which factors equality and inequality constraint. So which means already we have considered equality constraint, we have identified equality constraint, inequality constraint, and then now we have to form a argumented cost function. So argumented cost function C will be equal to, so if you have not forgotten, so you will know that C1 plus C2, right? So minus lambda, are you remembering lambda dash or lambda here? P1 plus P2 minus 550, like this one we have done, right? This is just a simple case, but here we have to consider a lot of problem, right? So now what we have to do is this argumented cost function will be given by C equal to, this one is C1 and this one is C2 minus argumented cost function in optimization. What you have to do is lambda dash dash again lambda into, so you have to write that equality constant P1 minus PL1 minus, okay, again minus lambda 2 because there are two equality constant P2 minus PL2 minus given by that equation plus, so from here till here will be an inequality constant which it is already specified in the problem. Okay, so that inequality constant, what how we have to do is plus this we have to introduce the penalty function, right? So penalty function P into P1 minus 3, because it has been written that P1 and P2 at the max it has to be sorry, not 0, P1 should be 3 per unit and P2 also 3 per unit, which means, so when you bring to the left hand side, so it will become minus less than 0. So which means penalty function for the generator 1 we have introduced this, then for generator 2 we have introduced this, again it has also given that voltage limit minimum and maximum. Okay, so for a generator 1 you have introduced penalty function P V1 minus 1.025. Okay, this is we are taking first maximum one, then P2 V2 minus 1.02. Again for generator 1 there is a minimum limit, it has been given P 0.975 minus V1 plus P 0.975 minus V2. Okay, so where we have to introduce penalty function, this is based on the optimization formulation, right? So now we have formed this. Okay, so this equation. Okay, so from the given problem, first we have to identify equality constraint, second inequality constraint. After that we have to form a augmented cost function considering all, then we are introducing the penalty function, and then we have, remember that penalty function P of t will be equal to e to the power beta t, where beta can be set to 100. Here I have set to 100, but it says that beta can be when you set the beta, it should be greater than 0. So this condition has been given earlier. Okay, so here I have set the 100 and it's all, but when I set to 100, there is some issue. Okay, so later on you will see, and then, but this one it depend on you. Okay, how to choose the beta, but when you choose the beta, it should not be less than 1, but it should, sorry, it should not be, it should be greater than 1, and then you have to keep on solving that. Okay, so 1 2 3, but it will be too tedious, so that's why you can choose one value. Let's say beta should be greater than 0, so you can choose 1 and then you do one iteration, then you choose beta is equal to 2, you do iteration, so it will next iteration, so it will be a tedious job. And then I have not done for all, but when I choose around 100, it's coming somehow near, okay, but there it violates, even though it violates some constraint, but even then it is coming somehow near to our solution. So that's why I have chosen 100. Okay, so but actual procedure is beta should be 1, then beta should be 2, 3, and then you have to go like this. But it will be too tedious. When it reaches to 2, 3, then you will know that there are huge difference you will find. Then you directly jump to 10, 20, and then you can see that how you can find. Okay, so but when you see the solution, you will know that. But after choosing this one, how you do? So step will remain same in the previous lecture. That is step lecture number 5. How to carry out the optimization. You have to differentiate that DC. Okay, you have to differentiate this DC by dP1. Okay, then again DC by dP2. Okay, then you have to differentiate DC by d lambda 1, then d lambda 2, and then V1, V2, and then all. Okay, so this one I have not done. Okay, but you have to do like this, and then we have to set all equal to 0, and then you have to form a matrix equation. Okay, then matrix equation, and then you have to solve and then find. Okay, so that's why I have written that we then set all partial derivative to 0 and solve the resulting equation to obtain the values of variable which result in minimum value of C. Okay, are you remembering that? Okay, so we have done that, and then this equation can be solved. Okay, this equation to be solved are non-linear algebraic equation and can be solved by, so this one you have learned that Gauss-Seidel method. So you say it will be easy to use Gauss-Seidel method and then you solve that. So here I have written you may try the same using gradient descent method. So earlier we have done, which is discussed in the previous lecture. Okay, so what we have to do is first carry out the derivative with respect to P1. Okay, then P2 lambda 1, V1, V2, lambda 1, lambda 2, and then you have to is equal to 0, then you have to form a matrix, and then it will be a non-linear algebraic equation. So you can, it will be easy to solve using a Gauss-Seidel method. So now with this, I know that you will find very difficult to solve this. So I have created some problem or some MATLAB program, so not problem. So you using a variant Gauss-Seidel method, and then you just copy paste and then see how answer it is coming. Okay, so I have solved in the MATLAB. Okay, so this one I solved, and then manually, if you want to try, you can try, but definitely I know you will not try. But procedure you have known how to carry it out. Okay, so you can use this and then see how it works. Actually, final answer you will get is this. P1 should generate 2.5982 and P2 should generate 2.99431. Okay, which means it is not violating our case. P1 maximum, it says 3 per unit. Okay, it should not go beyond. So now P1 is coming out to be 3 per unit and P2 also coming out to be 2.94, which is below 3 per unit. It is not violating. But here Q1 and Q2 you will get the answer, but we are not required to consider about the Q1 and Q2 because reactive power we have considered is unlimited or free. So here you may not, but when we solve this MATLAB program. So I have made such a way that you will get answer for Q1 and Q2 also, but they have not mentioned any constraint about the Q1 and Q2 because it has been considered that it will supply whenever require a reactive power. Okay, so that's why Q1 and Q2 will not care much, but here one constraint it is not violated. Okay, so then another one is voltage V1 is coming out to be 1.0062 and V2 is coming out to be 1.0263. Okay, which means see here, so maximum voltage we have to get is how much it has been given. So it has been clearly mentioned that voltage V1 and V2 should be okay 1.025. Okay, 1.025. Okay, so which means both the voltage at both the buses should be 1.025 per unit. It should. Okay, so now V1 it is not violating, right? But V2 when it reached to V2, so there is slight variation. So that's why I said that beta value will determine this all thing, penalty function, because we have introduced penalty function in the inequality constraint. These are the inequality constraints. So now this beta value will determine this. So what you can do is at least 1.025. So which means it's very minimum violation. So then I accept that. Okay, so I accept that. But if you really want to change this, you try to change the value of beta and then see that. Okay, so but V1 is not violating, V2 little bit it is violating, but we can accept that it is within the range, and then phase angular difference is minus 8 degrees. Fine, it does not mention anything about the phase angle. But our case is very important thing is we have to see this. This is not violating power. Fine, when you minimize that, it is not violating. V1, V2 is also at the acceptable range, but V2 slight changes is there. Then what we can say is the power flow from bus 2 to bus 1 will equal to 1.4413 per unit, and then losses will also be calculated 0.0395 per unit. Okay, so this is solution you will get when you if you are able, if you solve or run this MATLAB program. So you will get this, and then comment we will see. Okay, this is a solution you will get, and then this solution we have to interpret, how to interpret or a comment. So now it is cheaper to import some power from generator 2 for local load, okay, 4 per unit at the bus 1. So if local load is 4 per unit, then it will be cheaper for us to, okay, so cheaper for us to import power from the generator 2. Okay, but when you import, this implies that there will be some losses due to transmission, which will increase the cost. Because losses, it is generally, you have seen that 0.035. So now if you import, then losses will take place in the transmission line, which means so cost will also shoot up. Okay, another second comment we have seen. First comment is it will be cheaper. You can say that you can import from generator 2 at local bus, which will consume a 4 per unit at bus 1. But okay, so here what I am trying to say is, okay, so some of you may misunderstand that. So here bus 1 power, let's say, is 4, but bus 1 is generating how much? Maximum it cannot generate 3, it is a already set constraint. But in bus 1, how much it is generating? It's generating here 2.59. We will not be able to fulfill that. Bus 1 record 4. So then you can generate some remaining amount from the P2. But what it will say is, when you import, we have to be mindful about losses due to transmission. So if there is losses, definitely cost will also increase. Then another thing is, therefore we have to trade off, means obtain power from cheaper route generator, and at the same time ensure losses due to transmission error low. Okay, so this in this interconnected system, so always, okay, so we have to trade off, means obtain power from wherever there is cheaper one, you try to get from there. Okay, and then voltages at the two ends, voltages at the two ends can be adjusted so as to reduce the losses. So it means that when we obtain the power from bus 2, so there is losses. So now this can be adjusted by adjusting the voltage at two buses. Okay, so we can adjust these buses, a voltage at the two buses, and reduce the losses. But obtaining voltage power at voltages above the nominal result in lower losses due to lesser current, but then voltage have to be restricted within the limits. So now when we say that we can adjust the voltage at the both the buses and try to reduce the losses, but when you adjust the voltage, you have to be mindful that it should be within the range or the limit which it has been specified. So in our problem, voltage at bus 2 is slightly higher than the specified limit. Okay, bus 1 we don't have a problem, but bus 2 it is higher than the specified limit, that is 1.06. Okay, exactly I am not remembering now. 1 point how much? 1.0263, but actually it says 1.025. So this is slightly higher than the specified limit. So this can be corrected if the penalty function parameter beta is increased. Okay, so when I use 100, so that's why I said how to choose a beta is depend upon you. Okay, so beta can be greater than 1, so you keep on doing that 1, 2, 3, and see any other condition are violating or not. So when it reaches to 100, it is coming somehow near, but still then voltage at bus 2 is violating the specified limits. Okay, so but how you can do is you can correct this beta. Okay, change the penalty function parameter beta and try to increase NSC in the problem. However, when you change, this may cause divergence in the numerical method used for solving the optimization. Okay, so there is problem, but when you reach near to it, we normally we used to stop our solution. Okay, so this is the command or optimal power flow, an example of optimal power flow. Okay, so this is about the optimal power flow. And then next, still optimal power flow, but earlier what we have considered is we have considered that reactive power is unlimited or free. Okay, so which means whenever we require, we assume the reactive power is supplied. But in actual case, this reactive power will not be free. That's why you are using SPCs or StackCom and then all, right? But in earlier example, we have seen. Just to make you clear, we have considered, okay, first reactive power is free. Initial one, we have considered all are not a constraint. Then later on, we are trying to see 5 constraint. From 5 constraint also, we have seen that reactive power are free, no, and then unlimited. But in real case, these are not free and unlimited. Means in realistic power system, the following additional point have to be considered. Okay, that is reactive power capability is not free and unlimited, which means we have to pay that. Means when you pay, we have to charge that, right? You will not provide free. Whatever you do, it will be charged, right? So example, I am giving example. I will go a little bit away from the power system. So when you go for shopping in the shopping mall, okay, that owner will be charged electricity, house rent by a government or whatever it may be, tax and then on. But actual case, who is bearing this electricity bill, then tax and the house rent? Actually, real case is customer, because that price of example, one price of a jeans is, let's say, 5,999. In that 5,999, electricity charge will also be there included. Then house rent will also be included. Tax will also be included. So exactly like that. Even for power, so additional will not bear by system operator. Everything has to become to the customer only. But when you do the customer, as far as possible, we try to minimize. That's why reactive power capability is not free. Means we use we are required to buy the StackCom or SPC and a UPFC and so on, which means when you install, that cost will be involved. That cost from where you will recover from the energy cost, right? So this is not free, you have to know. But in earlier example, we have considered it is free. Then another, there are many additional controllable variables possibly having service costs like tap changing, tap setting of a tap changing transformer, SPC output, TCSC reactive, HPDC power flow, etc. All will have some additional controllable which involves cost. Means when you install this, you needed to pay. Then some operator has to come there and then perform that. Then we have to pay. So this involves the cost. So this also has to include it in the cost, your cost. Okay, so each controllable variable is likely to have a limit which is dictated by the stated equipment. Okay, so depending upon the equipment, it will have its own limit. So, and then another one is in current in the transmission line has to be within the value as dictated by thermal limit. So earlier one, we have not considered this. What we have considered is reactive power is free. And then we have not considered anything that extra device installed in the power system operation like SPC, HPDC, TCSC, reactance and then all. Again, this also we have not considered. current in the transmission line has to be within the value as dictated by thermal limit. If it goes beyond that, so again it will create a problem to the transmission line. Okay, so these all additional thing we have to include. So, and then another additional is security constraint. So when you say about the security constraint, don't misunderstand with the other security. Okay, here security means stable. Your power system should have stable and having a good power quality. Okay, this has to be there. But earlier one we have not discussed about the security. So now even if we have ensured that we have a least cost real power and reactive power for a given network and load condition, we would also like to ensure that this schedule is secure, which means you are getting the supply, and if it is not reliable, then definitely you will not like to have a power from that company. Or okay, so as far as possible it should be secure, even though your cost might be very cheap. So somebody will not opt your service because they will say that it is not reliable, you are providing at the low cost, even then we, so your service is not reliable. So normally they will go to the higher one, right, which will have a secure one. Okay, so this means that if there is a disturbances when the system is operating as per schedule, then it should be stable. Okay, that means it should settle down after a credible disturbances to a post fault equilibrium. So now what is mean by stability, you see the unit 2. Okay, so which means right after fault or some disturbances, it has to clear, right, fault and then get you back the power. So but whereas in our country sometime, so it will not, you will not get the light for whole night also, right? But we don't have an option because we cannot go for others. We have only one company who is carrying out the transmission and distribution. Okay, so that's why no option. But in other country there are different types. Okay, so then transmission line voltage and current constraint are not violated in the post disturbances steady state, which means right after your disturbance is there, this transmission line voltage and current constraint are not violated. Okay, sometimes we may see that your voltage is very high, right? So it should not violate. Right after disturbances, it should come back to the normal or within the limit. Okay, so with including this all, then we call it as security constraint optimal power flow. So earlier one we have only done for optimal power flow. If we include this all condition, extra condition, three condition, it has been written: reactive power is not free, and then there are costs involved in additional controllable device, and then current in the transmission line is within the thermal limit, and then security constraint. Then if you carried out the optimal power flow, then this type of optimal power flow is known as security constraint optimal power flow. Okay, so that's all about the optimal power flow security constraint. Okay, so example we will not solve. So for you all, this is more than enough. Okay, so now today what we have covered is we have covered about the optimal power flow, and then we have also carried out what is mean by optimal power flow, and then we have carried out the optimal power flow considering 5 constraints. Okay, that is control variable, load demand is fixed, cost is a function of real power, real power, then voltage magnitude, and then we have solved one example, and then we try to carry it out. But here I have not solved, just form the equation, and I have used this MATLAB program to find this solution, and then we got this solution. Even though there is little bit violating in the voltage constraint, it's fine, there is very minimal. And then you can improve it by changing the penalty function parameter beta. Here I have used only 100. Okay, and then you can see that. Then we have to consider another realistic. In real, this reactive power capability is not free and then unlimited. So then another additional control variables, current in the transmission line within the limit, and then security constraint. So if we consider this, then we consider as a security constraint optimal power flow. So that's all for today. And then with this, okay, so we'll not go further on the optimization. So which you will learn in the next semester, so optimal power flow. So with this, we will end up the optimal power flow, and then with completing the optimal power flow, so we are completing unit 4. Okay, so today we are completing unit 4. So from next class, we will study about the unit 5. So unit 5, study unit 5. So unit 5 is on preventive, emergency and restorative control. So unit 5 will be much easier. You have to know only the operating states of a power system. Already we have learned. So that operating states, based on that, we have to carry out the control. So then it will come preventive control, when you will do a preventive control, when you will do an emergency control, and when you will do a restorative control. So we have to know that 5 states of operating power system operating states. Okay, so that's all for today. And if you have any doubt, okay, you can ask. Okay, so any doubt? Or if you don't have any doubt, then thank you for coming online. And then we have completed unit 4. So tomorrow we'll start the
Thank you,
unit
sir.
5. Okay, so thank you for coming online.
Sir,
Thank you, sir.
thank you, sir.
Okay.
Sir, this slide, this lecture also missing, sir. Slide number 7, it's not complete, sir.
One I have uploaded in VLE, no?
Yeah, that one received, sir. This
Okay.
current lecture.
Okay. I will once more I will check and then upload. Thank you for.
Okay, sir.
Okay. Thank you for coming online.
Thank you, sir.